Let's move on to our next speaker from Kring et al., who will be talking to us about an exploration operations system for Artemis. Thank you.
Thank you very much, Amanda. I'm going to turn off my video so I have better bandwidth for the audio. Still waiting for my slides. Thank you. Can we go to the next slide, please? Okay, so I want to begin by reminding everybody of Apollo and Constellation lessons, and I know that this is a popular theme this morning. So Artemis can obviously draw on the Apollo program and its 6 human landings, and you heard more about that from Jim and Jack wonderfully today. But something that's sometimes overlooked is that Artemis can also draw on the Constellation program, which conducted 6 years of study, training, and mission simulations for a modern era of lunar polar exploration. Very much like that is which is anticipated for phases 1 and 2 of Artemis. Constellation, like Artemis, was targeting the lunar South Pole and that impact crater terrain. Next. So from that experience, we suggest 8 operational tenets. First, to integrate science and engineering. Second, craft lunar surface operations in a framework of an exploration plan. Integrate robotic and human exploration. Produce well-trained crews. Provide crews with appropriate sampling tools. Conduct integrated lunar surface mission simulations. And collect lunar samples with every mission because they truly are the key to transformative lunar science, and engage not only the international community, but the academic community. And I want to step through each of these briefly in the next few minutes. Next slide. So lunar surface expertise resides in a planetary science community and should be embedded in the exploration process. NASA's Solar System Exploration Research Virtual Institute, which already integrates S&D and HUMD Directorate, could potentially be expanded to meet that need. Constellation programs like the Directorate Integration Office, Lunar Surface Systems, and Desert Rats could be reestablished into a coordinated network of activities. Next. We need to develop lunar surface operations in a broad framework of exploration plan. I mean, initially, Artemis 3 is going to focus on a safe landing, return of crew, and initial polar science. But future missions will need to be prepared to explore a much more diverse set of geologic processes and potentially in situ resource utilization. Science and exploration are evolutionary processes, so we need to build a system that can accommodate that. Here, for example, is a map that contains 5 potential landing sites that are in the design reference mission plan in the global exploration roadmap. And the geology and the EVA plans for each of these sites will obviously be distinctly different. And we need to prepare now for that evolution in EVA plans. Next. It's important to integrate robotic and human exploration. Robotics is incredibly useful. They can be used to validate precursor data, reduce risk requirements and human exploration costs. That's the type of thing that Viper is going to do. They can go to hazardous locations that crew cannot access, such as deep within a PSR, and they can expand geographic distribution of exploration sites. For example, on the left there, you see a telerobotic survey for subsurface ice that could be conducted by a lunar terrain vehicle in between crew landings. But it's important that robotic assets not be used to conduct the types of science and exploration best done by well-trained astronauts. Next. Now, in addition to surface EVAs by crew, it's important to understand that this robotic and human integration can involve human-assisted sample return missions. Here, for example, is crew in the Gateway teleoperating a rover on the lunar surface, which collects samples and then returns them to an ascent vehicle that carries them back up to the Gateway. Next slide. This type of teleoperation is something that's been tested already on the ISS. Here you can see 3 NASA and ESA astronauts teleoperating NASA's K-10 rover in the NASA Ames test facility. So this is a technique or capability that's already under development and in testing. Next. You've heard this before, and I can't emphasize it myself enough. You have to produce well-trained crews. The most efficient and productive asset in space exploration are well-trained crews with appropriate tools. Geologic training of Apollo crews was an essential element of their success and will be even more essential in longer duration Artemis missions. For the initial Artemis missions in the impact cratered highland terrain of the lunar South Pole, training should feature impact craters such as Meteor Crater in Arizona and the Reese Crater in Germany, and locations with highland lithology such as the Duluth Complex in Minnesota. Next slide. I want to point out that the South Pole resides on the rim of an impact crater, Shackleton. That impact event excavated 10 to the 11 cubic meters and nearly 1 billion metric tons of rock that were deposited on the crater rim and surrounding terrain. Activities in that area will be on impact ejecta. Knowing which rock samples to collect from those deposits takes skill that will need to be developed. Wherever the Shackleton impact event and other impact events in the region modify the distribution of volatiles. Understanding those impact-imposed consequences and evaluating them while engaged in EVA also takes skill that will need to be developed. Next slide. They need, obviously, appropriate geologic tools. Here you can see a set that was used by the Apollo astronauts and another set that's being tested by Don Pettit and the MBL. One thing I want to say at this point is that we want to avoid burdening crew with devices for measurements best made on the Earth. Give them the tools they really need and nothing else. Next slide. We need to have integrated mission simulations. Such simulations are an extended part of the crew training program and must involve all anticipated participants in lunar surface missions. This is something that we did very well in Constellation and something that I hope we can stand up for Artemis very soon. Next slide. And finally, or not finally, second to last point, I want to point out that lunar samples are not just gray rocks. They are the best evidence for generating the greatest progress in our scientific understanding of the lunar surface. And moreover, can oftentimes lead to very important exploration findings. I show here a few of the big ideas that came out of analyses of the Apollo collection, including the detection of water in Apollo 15 and Apollo 17 glasses, which now leads to our wish or desire to harvest water for crew consumables, radiation shielding, and propellant. Next slide. And throughout this process, I hope that we use important collaborations. We should utilize the tremendous expertise that exists in the academic community. NASA does its best science when collaborating with the nation's universities and research institutes. It's important, too, to engage the international community. Such collaborations were an integral part of Apollo and should be a part of Artemis. People sometimes forget that the first chemical analysis in an Apollo sample was done by an international partner working at the MSC with Apollo 11. Such collaborations include astronaut training, flight hardware, implementation of missions, and post-mission analyses. Next slide. So in summary, let's use the lessons learned in the past and implement these 8 operational tenets. Again, they are to integrate science and engineering, craft lunar surface operations in a framework of an exploration plan, integrate robotic and human exploration, produce well-trained crews, provide crews with appropriate sampling tools, conduct integrated lunar surface mission simulations, collect lunar samples on every lunar surface mission, and engage the academic and international communities. Thank you very much.
Thank you so much, David. That was incredibly informative.